Okay, looking at number 3 here, I've given an equation with a very negative delta G, so it very much says spontaneous. But it says that we have this acetylene and we store it for a year, but at the end of the year, the sample remained unchanged and there's no graphite or hydrogen. So it's saying it never went forward, even though this says it's spontaneous. All right, so we want to know why that is the case. All right. This is kind of neat because it actually kind of introduces us or explains us the importance of understanding what delta G is. So delta G does say spontaneous. This says spontaneous going forward. Going forward. I'm going to write that out. Going forward. All right. That doesn't necessarily mean that doesn't necessarily tell us anything about how fast it goes. All right, so what I mean by that, we saw in previous chapters we had rate laws. And for this one, it would have just had that C2H2. Now, we don't necessarily know the exponent. We have to experimentally determine that, and that looks like an O, so I'm going to put an M there. So we would have to experimentally determine the actual rate of this reaction. Now, technically, once you have the rate, and especially if you do it a couple times, you could actually figure out something we referred to as the activation energy. That was when we took two different Ks and did the natural log, and the activation energy divided by R was kind of that slope of the line that would have been made with this equation. Now, that was kind of important, because while this delta G does just tell us if we start at reactants and we go to products, there is a decrease of energy, which typically is what we see on that spontaneous reactions. That is exactly what we see. But the activation energy is kind of like the hill on this reaction. It's the energy we have to put into it before we can get to those products. And that's what's happening here. So the reason the acetylene is still stable and nothing's happened to it is because it was properly stored. It's actually kind of like the gas in your car. It's able to actually make your car go very fast, very quickly with just put into the engine the right way. But as it's sitting there out in your car, it's not burning. It's very efficient at turning into energy, but we have to actually start the reaction. We have to actually put that activation energy into it. And delta G's don't tell us anything at all about the size of that hill. There are reactions that are spontaneous and have a very short reaction, or very small activation energy. Those are typically things that kind of explode. Now, I mentioned that properly stored. That would factor in here because it turns out acetylene can be improperly stored. I know I can go to most hardware stores and I can buy acetylene torches. If I grab that and kind of shake that container or invert it, it will sound like there's a liquid in there, even though this says it's a gas. Typically, acetylene is stored in acetone, which allows it to not react with itself. But if it was just straight old acetylene, just like even in a balloon, if you put it in something and let the pressure build up too much, it would no longer be properly stored, and it would very rapidly turn into something else. And actually, in the atmosphere with oxygen, it's going to turn into carbon dioxide and water. But very exothermic, that would be kind of an explosion. But this is not happening because properly stored, we're not giving it any energy. No activation energy, so it can't go to make our products.